Hello everyone, Dark here, and today I'd like to show you my flip display in Besiege. What I'm going to be showing you is what the display is made of, what code is in the blocks, and how to convert a video to support this format. As far as each dot on the display, it is only comprised of a pin, a steering hinge. The steering hinge here you can see uses the variable names or whatever for the inputs. I have auto return, and then the logic extensions mod allows me to set FPIO, which allows it to flip it back instantaneously. I also have the no boundaries mod, which allows me to set the rotation speed to something ridiculous. And then you can see the limits there. What it also comprises of is just a normal wooden block in the middle that's been shrunken down, and then two of the metal armor with these yellow and black skins on them to be able to do the different colors. And then from there, it's just 9 rows of 16 dots, so a total of 144 pixels. The reason I started with this size is that it was the size I was comfortable using in terms of frame rate. As you can see, I'm limited. I mean, I usually play at 144, but I have it limited to 60. But if I press play, you'll see that it doesn't like it so much. I could still manage it just fine. Plays just fine. It's just, I prefer more consistent frame rates, and you can see it's dropping below 30. So if I drop it down to like 50, it's a lot smoother. Though there's still a random hiccup I'm encountering with the game engine. I don't know why it's like getting hung up every now and then. You might have seen that in the original video. I also need to fix, for some reason, there's 3 dead dots here. But that's probably something with the code. And last thing I noticed was it looks like the first 3 pixels are actually the last 3 pixels, and it's just offset for some reason. But I'll look into how I'm converting the data to see if that is a problem that's causing some problem like that. So the reason I think this causes low FPS is because each dot is 5 parts, and then there's 144 of them, and if you do some quick math, that's 720. So that's a lot of parts. And yeah, as far as the processors, here you can see the 10 total processors I have. This one is the main display control, which means this is decoding, well, not decoding, it's pulling the data frame information and sending it to all these controllers. The reason why I have so many instead of just one is because each code block does not support more than 100 variables, meaning the same value of a key press or the named variables now. It only supports 100, and I need 144 just for display. So I did each row of pixels has its own controller. If I wanted to, I could probably actually lower this. So if, say, if this is only 16 right now, and I can go up to 100 plus an input, so 99, I could probably manage 5 rows of pixels off a single controller. That might be easier, but I don't know. I figured that maybe having, I don't know how heavy the code processing is on the game engine, but I just kind of assumed that maybe if I had more of them asynchronously pulling data, it might have an easier time with that, especially since the data that's coming out of here, I'll show, is only 9 variables. So it encodes it into from the binary to decimal technically. So you have all of these which have a different value. These are all decimal with so like each of these values is a row, and that value is sent over this. These are only support floating point numbers, but by going up here, you can see I divide by 100,000. What that does is it pushes the value 5 decimal places to the right, and granted they're floating point numbers, but the precision on them is enough that I can go up to about 10 or 11 digits before it starts losing precision. So this, technically, the data going over these connections is perfectly accurate. Granted, I don't have any like error correction, but that's fine. And then here I'm showing the input, and then these are all the outputs. So as you saw earlier, where I had the numbered variables, and then I just do 0, or I do the first number is the row, and the next two numbers are the pixel. So you can see like 004, 104, 204, etc. And then this is just pulling in the values. So what it's doing here is it's multiplying it by 100,000 to bring it back up to an integer, and then toString2 converts it to binary. So now we have a binary string, and then if the number is too low, it doesn't have preceding zeros, so I just add those with this. And then from there, I can split it into an array and then go over the array. So this is going over each pixel one at a time. So it sends an out value through these. So it outputs a value to each where the index is +1. So in this case, it would be 1, 2, 3, and then the value is the 1 or 0. So setting it on or off. Technically, I can also set it to an intermediate value, but that's just something that's not necessary here. Though it does open up possibility for like, what if I maybe had a 4-way, so I can have 4 colors, you know. I also am going to, in the description, supply a GitHub repo that has all of this code and information, so you can understand how to load this and use it for yourself. So this is where I show you the code I use to convert it into a format that is suitable for this display. First of all, it starts with taking a video. So like in this case, I downloaded using YTDLP. And then what I had to do was use FFmpeg to convert it. I forgot to save the... Okay, here it is. So I'll also provide this in the GitHub, but here I'm taking the video from YouTube, which is just a WebM, so it's VP9 plus Opus, or in this case, AV1 actually. Or I don't know, anyways, doesn't matter. What I do is I use the video filter scale. So what I'm doing is I'm converting it down to 16 by whatever. So in this case, it would be 16 by 12. So width and length, height. This video originally was 960 by 720. So bringing it down to 16 would be 16 by 12. Obviously our display is not 16 by 12, but 16 by 9, but we can do math later to solve for that. The only thing to note here is that FFmpeg doesn't like when you use odd numbers. So if you run into a 16 by 9 video and you're trying to convert it to 16 by 9, it will not like it. So you might need to do some either scaling it differently here, like I kind of do since it's 16 by 12, and then cutting off the rows of data. So in this case, I'm ignoring the first and last 2 rows of pixels. And then from there, we have flags neighbor. So this is nearest neighbor scaling. And as I can show you here, this results in, oh, I can't show you because they're raw, whatever. Basically, it doesn't approximate the pixels. It'll just, whatever pixel is below it, technically, it is just pulling the raw value. It's not trying to approximate and smooth. It's just raw, blocky values, which is why it works for this, because that's what we're working with. We're working with very blocky yellow or black color, so it works better that way. Pixel format is RGB24. What this does is it ensures that it's red, green, blue, so 0 through 255 of each channel, color channel. We don't have color channels here, but we'll solve that, though I probably could have used the color format that is grayscale, but that's fine. RGB24, this just means the total bit is 24. That's total number of bits, so 8 plus 8 plus 8, so RGB. And then we output it into a raw file. So this is just raw data. There's like nothing else with it. If I were to do, I can't even do MIDI info on it because it's just raw data. Yeah, and then we have all the frames here. In this case, it totals to only 3.6 megabytes for the whole entire video. It's a 3-minute video, 3.5-minute video. So this code I will include on the GitHub, linked below in the description. But basically what we're doing here is we're taking now those raw frames that we exported here and now processing them into a data format that is supported by our display. What we're doing here is we have the file path. So we're pulling in, first of all, our data file. This is where we're going to write to. So if I go back here and I go to my data file, you can see this is how it's writing the data. Our data is an array of 9 numbers, and then this is a frame. This is a whole frame. Each number represents a row of pixels, and like I said before, with the binary encoding, each number is a 16-bit number, so it goes up to 65,535. So it's just basic binary. So if we had a 16-bit number, it would be 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 40, 96, and then 8, 192, and then 16, 384, and then 32, 768. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bits. And the way this works, if I go to the other data file and I scroll, you'll notice that a lot of the numbers are really close to 65,000. Basically what we're doing is, the way binary works is we're adding up all these numbers to equal this number. So I'm taking advantage of the way binary works to use our display, since we only have 1 bit of information per pixel. And the way that binary works is it just toggles on and off for each value. So I don't know what it actually is, but if I do this, you'll start to notice the pattern of binary. And I can actually calculate this number once I am done doing it. So let's do this real quick, because this will be a better demonstration than trying to decode. So 2 plus 8 plus 128 plus 256 plus 1024 plus 8192 plus 32 768. So that's 42,378. So as you can see, I was able to create a string of binary into a number. So this is the number that I send over from the display controller to the row processors, which processes each row. And then, so in this case, what you would see on the display is a black pixel, a yellow pixel, black pixel, yellow pixel, black, 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 yellow, yellow, black, yellow, black, 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 or black, black, yellow, black, yellow. Anyways, but hopefully that makes sense. That's how the encoding works. And that's what each value here is going to be. So now we can go into how this actually does it. So when we read the directory of frames, so this is the out directory that I have here. So it'll read all these frames, and for each file, it will go over them. So this is going over each file. The files here are just a name, a file name. So we have to actually read the file. We have to pull the file data. It gives us a buffer. And if we pull it to JSON, I'll show you real quick what it looks like. So if I run this for like a second, there you go. Actually, I'll let it run a little bit longer. There you go. So you can see here, we're getting a buffer with a lot of data. This is 512, I think, or 576. Yes, that's correct. So you see here, 576 bytes. This is literally bit for bit data. There's no headers or anything as far as I understand in raw. So we literally have raw frame data of each pixel. So what we then do, we have a loop here, which allows us to compile the data. The way this works is, if we look at the data here, the first 3 numbers, this is RGB. So like I said before, this is an 8-bit number. If you do 8-bit, 8-bit is 8 numbers, so 2 to the power of n. So in this case, 0 would be 1, so 1 plus 2 plus 4. So that's 3 bits, 8 bits, 3 bits, 4 bits, 5 bits, 6 bits, 7 bits, and then 8 bits. So 255. So you can see that's 8 bits of information. RGB. So this is our RGB 24 right here. So what we do because of that, we know it's every 3 indexes on the array. So RGB, we can do modulus 3 for compiling the current bits. So the way this works is it adds the current value that we're pulling. So in this case, let's say 253. It adds it to the bit. So now the value is 253. And then it loops again because it skips over both of these if statements because it's not triggered by 3 or 47 because you can't, divide 1 by 3 and 1 by 47. So it goes back, it adds it again. So we have 253 again, 253 plus 253, and then we go through a third time, 253. Oops. That makes us have 759. So then what happens when it goes around the third time is, say this is the third, technically the fourth time, but it's index 3. We're pushing the current value, which was from the previous loop, which is our current value would be 7, we just calculated it, 759 divided by 3. So if we do 759 divided by 3, that'd be 253, obviously, because that's how you average. So 253 is greater than 127, so we push the value 1. What this is doing is we're doing what's called binarization. So if I go into Clip Studio right here, and I'm gonna, thankfully I have the powers of editing, so I can blur things I accidentally show. But if I go to my pictures and I pull, let's say this is an emoji that I have. I go to correction layer and then binarization. You can see the value here. This is exactly the same thing. So this goes 0 to 255 because it's 8-bit, and 127 would be the middle point. So you can see what happens is if I toggle this, you can notice this area is generally darker and this area is generally much brighter. So it's turning the slightly brighter and higher values just into pure white, and it's turning the slightly darker or black values into pure black. So that's literally what we're doing with our math here. And that's the same, basically the same algorithm that's working right here when we have this, and we can adjust the value, and there we go. So we're adding 0 or 1 to our current row. So our current row, as I showed, a row of pixels that goes up to 16. And you can see that here, 47. Why 47? Because we have RGB data. If I do, it's technically 48 because if you include 0, it's a length of 48. Divided by 3, we have 16 pixels. So because we're iterating over each RGB value, and each RGB value is 3, we do 3 times 16 and we get 48. And then including the index of 0, it's 47 because we do -1. So this is on every, when we hit an index value that represents the entirety of a row of data. So in RGB, that would be, again, 48 numbers, but we are technically doing 16. This is where our 16 comes in because we're compressing it down every 3 indexes. We are setting a bit value, which is going to be we're going to grab the current row and iterate over each pixel. And what we're doing here is we're adding to the bit value. So just like I showed you, this is the part where we're encoding the binary into our decimal representation of 16-bit. So yeah, just like I showed you before, if I go back to the calculator, say we had just the first and last pixel are highlighted. So that would be 1 plus 32768. So 32768 plus 1 is 32769, and that would turn on the first and last pixel. There is a name for this. I don't know what it is, but you're basically it's a map. Basically, that's not the right term, but it's the only way I can think to describe it. It's just we can use just like hexadecimal. So you might have heard hex codes for colors. We have a random color, right? We have RGB 255, right? So red is 255. It's mostly red, but there's some green, so it's orange. And there's a hex number here. If we were to convert this, basically F is 16. So if we have FF, that's 16 times 16, which is, oh, I can't do this math off the top of my head. 256. And as you know, we have 8-bit RGB. That's 0 to 255. So FF is representing 255 here. So that's how hexadecimal 2 binary works, basically. It's the same type of thing here. We're just encoding it in decimal because our code blocks only support floating point numbers. So I'm able to encode the integer as a floating point number, which is this number, and then decode it on the other side back into binary. Sorry for the tangent, but we're going over each row, and if the value is 1, so if it's not 0, so if the pixel's not off, we're going to determine which place this pixel is at. So the way this works is we're actually doing right to left. The index is going from 0. So 2 to the power of 0 is 1, right? So if we do 32768 divided by 1, it's just 32768. And that's where this comes in, where we have 1 here. So say 2, we don't have it, just like here. Next one, 8192. All we know is that it's true, so 1. But we're already at index 2. So 2 to the power of 2 is 4. So we have 4 here now. And then 32768 divided by 4 is 8,192. So say the first value was 32768 because, as I showed here, we have 1. We would just be adding 8192 to our existing 32768. So if I just do plus 32768, we have 4916. And then again, this would go on for the array of pixels, and it would turn out to be a number like this. And then once we're done with that, we're pushing the value to our new data. New data in this case just means a single frame of data. So I should really call this new frame. Actually, I'll just do that right now. New frame. That makes a little more sense. So each frame, as I mentioned, is a 9 length array, and this is just each row. So this is the first row, this is the second row, third, fourth, fifth, sixth, seventh, eighth, ninth, right? And that's our 0 to 8, just like in the game. Over here we have 0 to 8. So if I open this back up, it would be flipped, so it would be like this, but it's literally just pretty much just that. We would have 32641 in here, 65409 in here, 65408 in here, 65472 in here. This would take that number. So in here, it's the floating point, so we move it up and then we convert it back to binary. So we're just converting it back to this string. And then we can, as I said, display it on the screen. And then from there, what it's doing is, this is just the same thing as before, where it's just, this is every time it's just adding up these, like I said, and then we're doing append to file sync. And then that's where you get this data file that I was showing before. This is all of our encoded data. This is the equivalent, basically. This is still technically compressed data. It's on a bitmap. It's kind of a bitmap in that we're mapping rows with decimals, but it's not the same really. So this is just raw frame data. And then all we have to do here is Control A. Well, before that, what I did was I added a bracket at the beginning and then a bracket at the end. And then I recommend putting a semicolon. This is just because we're actually have an array of arrays, so a 2D array basically. It's just that the array here is representing the entire film, the video feed, and then each one is a frame. So all we have to do is we have to copy this 300 megabyte file, or this 300 megabyte data, into this data field here. So you can see this is very simple. It's literally just iterating every 30 FPS. So this is just the frame rate that I've currently set. I can't really go higher than about 50. It starts skipping and locking up. But anyways, you just paste it in here. Unfortunately, this editor doesn't go that far. It's limited, but the data is there. It's just not showing it. And yeah, that's it. I do recommend probably making a copy of this code. But yeah, you just paste it, and then once it's pasted and you have everything configured correctly, if you just press play, it'll start playing. And there it is. Thanks for watching. If you liked the video, make sure to press the like button, and I'll probably be making more videos like this, so feel free to subscribe.